You got it? I'll begin. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to help us to understand a little bit more about your creation today. Lord, in your name I pray. Amen. All right, so today we are talking about subgroups and isomorphism again. So let's get to it. So what is a subgroup? Definition. A subgroup rather H. Poor planning on my part. Definition. H is a subgroup of G if H is a subset of G and H is itself a group with respect to the operations of G. We write H less than or equal to G when H is subgroup. All right, notice the difference. This is subset. This is subgroup. All right. So, first example, how about Zn? Is Zn a subgroup of the integers? What do you think? While you're thinking about that, two really silly examples of subgroups. One is H is just the set containing the identity of the group because, well, it's closed under multiplication, inversion, it's associated, it's got all it takes to be a group. So there you go, it's a group with one thing in it. That's one possibility. The other entirely silly possibility is H is equal to G itself. G is a subgroup of itself. If the subgroup is not equal to G, it's said to be a proper subgroup. If the subgroup is not equal to the set just containing the identity, it's said to be a non-trivial subgroup. Again, my question, is Zn a subgroup of Z? Now here, of course, I'm talking about with addition and with addition. What do you think? The answer is no, it is not a subgroup. These are not even subsets. This is a set of sets, right? This is just integers. These aren't even the same object type. Zn is not a subset of Z. So no, it's not a subset. In contrast, if we were to look at H equal to, say, 0, 2 as a subset of Z4, then you can check that the set of elements 0 and 2 forms a subgroup of Z4. Right? 2 plus 2 is what? 0, yeah. So it's its own additive inverse, and that's pretty much it. Now, we have a theorem, which is ever so useful, called the one-step subgroup test. Dr. Sprano is happy that I am emphasizing this again. Last year I followed a book which had sort of suppressed this in favor of a two-step subgroup test, which is, by the way, on the same page a little later. And the one-step subgroup test is as follows. Here it goes. Let G be a group. If H is a subgroup of G, subset of G, and H is not empty, then H is a subgroup of G whenever we have the following implication. Here's the implication we need. If A comma B are in H, then AB inverse is in H. So if you can show what I'm about to underline in red, if you can prove that that is a feature of your alleged subgroup, then in fact it is actually a subgroup. But we also do need that it's non-empty. Right? Now in additive notation, what's this look like? A minus B in H, right? If we were working with an additive group, that's what that would look like. So here's the proof. So if H is a subset of G and H is non-empty, then there exists X, let's say, in G, in H, right? If it's non-empty, there's at least one element. Correct? And if there's one element, hence X. So assume, I'm sorry, I'm muddling things here a bit. We wish to assume the implication. Okay, we're going to assume this condition. We want to show that the condition star, the one-step condition, implies what? Implies H is a subgroup. What's it take to show H is a subgroup? 4 things, right? We need closure. We need identity. We need inverses for every element, right? And what else do we need? Associativity, right? So assume star. Notice X. X times X inverse is equal to what? It's equal to E, right? But by, what is it? So I'm trying to use the star here. I've set A equals to X. What is B equal to? X inverse. I'm sorry, I'm confused all of a sudden. Something I fail to appreciate. Oh, I'm sorry, guys. I have a mental block here all of a sudden. Somebody help? So what we have is the assumption that whenever A and B are in the subgroup, then AB inverse is in the subgroup. The trouble I'm having mentally is how do I know that oh, I'm an idiot. It's A equals B equals X, right? So by assumption, X inverse equals to E is where? It's in H. I'm sorry, I'm my own worst enemy. So just take A equals to B equals to X in star. In my mind, I talked myself into B being X inverse, which begged the question that I couldn't answer, if you're wondering. Not that that matters. You're not required to understand my confusion, okay? Not usually, yep. Do A and B have to be the same in H? No. But they are, in this case, because I'm taking A and B equal, that gives me X inverse is in H, but X inverse is also the identity by their construction in G. Yeah. But no, I mean, certainly not. I'm using the case that A and B are both equal to X for this case, for the purpose of this proof. Now, Also, if you look at HE, it's equal to H, and that's equal to EH for all H in H, since H is a subgroup of G, right? And E is also the identity, in G, right? I mean, there's only the identity here, x times x inverse is the identity of G, and this is what G does. What the identity does in G is any element times E is the element again. And that's still true for H because H is a subset of G, right? And associativity is proved in a very similar way, right? You know, if we have H1, H2, H3, it's equal to H1, H2, H3, since H1, H2, H3 in H implies that H1, H2, H3 are also where? In G, right? Because H is a subset of G, which means everything that's true for elements of G is also true for elements of H. Yep.
How do you know that the identity has to be in that subset of G?
Because we're assuming the condition star, the one-step test, and when we set A and B equal to x, that gives us x inverse, which is equal to E, which is, and so that, let's see here. That implies that the identity is in H. We still should show what? That we got associativity. I've just proved that the identity is still the identity. Like, it's nothing weird, like the subset has a different identity somehow, right? Still the same identity works as the identity. Associativity. What about closure? If A and B are in H, then notice that B inverse is in H. How do I get that? Why is B inverse in H? How about this? Take A equals to E, then A, B inverse is an element of H, right? Well, equals what? Equals B inverse is an element of H. So once I find out that the identity is in H, then it's pretty easy to prove that the inverse is in H. If I just take A equal to the identity, that gives me that the inverse of B is in H, right? And then, finally, closure, so that I've inadvertently proved closure of inverses on the way to proving closure of multiplication. How can you prove that AB? I'd like to prove AB is in H. How do I get that? Right. How about AB is equal to A, B inverse inverse? Which again, since A and B inverse are both in H by the one-step condition, A times B inverse inverse is in H, which is to say that AB is in H. All right, so I need to get Dr. Sprano to stop talking to me before class. It's it's not a good way to enter a class period. So I do best if I'm not talking to people right before class. I'd probably still mess this up even if I was just sitting by my lonesome playing Legos for the last hour, but I mean, I think I have said all the things that are true that need to be said to prove this, but I think you could have said it in about 30% of the time. Okay? So. If I was wiser, I probably would have just copied down what's in my notes and it probably would have been fine. What's the two-step test? Two-step subgroup test is if H is a subset of a group G and H is non-empty, then if 1 A, B, and H implies that AB is an H, and 2, A and H implies that A inverse is an H, then H is a subgroup of G. All right. I will not attempt to prove that, but it's easy to prove. And also, so you're like, well, which one should you use? If you want to prove something's a subgroup, how should you proceed? Do you want to use the one-step test, or do you want to use the two-step test? Like, both of them are mislabeled, right? Because they're at minimum a three-step test or a four-step test, because there's other tests going on here that are usually need to be attended to for a specific example. One of the things that needs to be verified is that it actually is a subset, right? That'll stop us dead in our tracks, like my first example. And I showed by your lack of, barking back at me about this, that obviously maybe figuring out something's a subset of something else might be more confusing than you realize or first appreciate, right? Because this Zn has the appearance of being a subset, but if you search your heart, you realize it is not a subset. They're different, Republican, conservative, right? So, sorry. Obligatory. Sorry. And also the non-empty has to be checked, right? So if you count showing a subset, showing non-empty, you still got either the one step or both of these steps to check. There really are 3 or 4 things that need to be attended to prove something's a subgroup. Now, personally, I find the one-step subgroup test is useful, and it'll work for me a lot of times, but there are certain problems that the calculational details of just make the two-step subgroup test an easier path, because it's easier for me to divide and conquer, figure out this problem, figure out that problem separately, right? The truth of the matter is, once you figure out those separately, you will be able to give a one-step proof if you want to, but anyway. All right, enough about that. So here's an example, 2.4.7. So let's let our group be GLN R, so n by n invertible real matrices. And then let's let H equal to A in R n by n, such that the determinant of A is equal to 1. All right? So is that a subset of G? Right? It should be clear that this is a subset of G, since why? The determinant of A equals to 1 is not equal to 0, so therefore A is in GLN, right? What was the definition of GLNR? It was the set of non-zero determinant matrices, right? Equivalently, the set of invertible matrices. So matrices with the determinant 1 are a special case of that. All right, so subset check. Observe the determinant of the identity matrix is equal to 1. Therefore, the identity matrix is in H, which apparently is non-empty. Check. So we've shown that the subset H is non-empty. What's next? Let's do the one-step test. We'll go one step. Let's one-step it. Let's see here. Is there some kind of stupid dance that goes like this? It's like I'm one-stepping. Is it? Is that a dance? No? I shouldn't be doing that here, right? Not without music. I mean, there's the music in my head, but it doesn't count. Let's see here. AB, element of H. Then what's that give us? The determinant of A equals to the determinant of B equals to 1. How about the determinant of AB inverse? Consider. The determinant of AB inverse, by properties of determinants that we know and love, is the determinant of A times, well, divided by the determinant of B, right? Properties of determinant, which is also known as 1 over 1, aka 1, so thus AB inverse is an element of H, right? Think of H as a secret club. In order to get in, you must prove you have determinant 1, right? So AB inverse is in the club. All right, and so there you go. One-step test, theorem done, thus. Therefore, H is a subgroup of G by the one-step test. Okay? In fact, this one is so important that it gets a name. This is the so-called special linear group. All right? And definition, if R is commutative ring, then SL and R is equal to the set of A in Rn by n such that the determinant of A is equal to 1. This is a subset. Oh well. I tried. This is, of course, a subset of the GLN R over a commutative ring we defined the other day, right? And essentially the same proof can be used to show that that's a subgroup of GLNR. Yes?
For the SL and then N and R, is that a regular R or like a real numbers R?
So let's see here. For example, if we were to look at SL2Z, this would be A, B, C, D, such that AD minus BC equals to what? Right? This so-called unimodular. I don't know what it's called. Anyway, SL2Z. 2 by 2 invertible matrices with integer entries, determinant 1. GL2Z, of course, also has the determinant minus 1 ones. All right. Moving along here. So next couple of constructions I have for you guys are more general. Actually, this definition I'm about to make is one of the more important ones I'll say today. Cyclic subgroup generated by G in a group G is bracket G bracket. I mean Langle G Wrangle. And that, by definition, folks, is G to the n, such that n is an element of Z. All right? Or, additively, what would this be? In the additive case, that's the cyclic subgroup generated by G. Of course, this would be a rather poor choice of name if it wasn't actually a subgroup, right? So theorem, if G is in G, then the cyclic subgroup generated by little g is, in fact, a subgroup of G. We can prove this pretty quickly using the one-step subgroup test, I think. First of all, by construction, this is a subset of G, right? Because if you look at it, what we're looking at? We're looking at powers of G. Is there any way you can take a group element and power yourself out of the group? No. So G to the n is necessarily in G already. So it's definitely a subset. Is it non-empty? How about G? G is an element of this G, right? Since G equals G to the 1. So it's definitely non-empty. So what are we, let's suppose we have x and y. Oh well, I tried. Suppose we have x and y in Langle G, Wrangle. What's that mean? If x and y are in this alleged subgroup G, what's that mean? There exists j and k in the integers, right? Such that what? How about x is equal to g to the j, and y is equal to g to the k? Hence, y inverse is equal to g to the minus k, and x, y inverse is equal to what? G to the j, g to the minus k, also known as g to the j minus k, which is an element of what? This is, again, an element of the cyclic subgroup generated by G, since what? Since j minus k is an integer. And hence, G is a subgroup of G, as claimed. Again, by the one-step subgroup test. I don't want to write that out again, if you don't mind. I would like for you to write it in proofs. Yeah. Any questions about that? So this is one way we can generate subgroups in a given group. Just take an element, and you can form the cyclic subgroup generated by that element. So there's always a way to create all kinds of subgroups in a group, right? We can always just use this construction to do that. Now, a couple of other terminology, which we'll spend a whole other lecture on. A group is said to be cyclic if what? When do we say a group is cyclic? Well, I'm erasing this. A group is said to be cyclic if it's got some element in it such that the cyclic subgroup generated by, let's say, X is the whole group G. So, for example, just to give you a flavor, Z4 is cyclic. And you could say that's generated by 1. You could also use the generator 3, right? Because if you look at it, it's 1, and then 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. There you go, that's all of Z4. So we can generate all of Z4 just by repeatedly adding 1. Another example, U5, which is 1, 2, 3, 4, right? Let's pick on 2. 2 to the 1, 2 to the 2 is equal to 4, 2 to the 3 is equal to 8, is equal to what? It's equal to 3. 2 to the 4 is equal to 16, which is equal to 1. So if you look at it, U5 is generated by 2. So both Z4 and U5 are cyclic groups of order 4. The choice of generator is not unique. Anyway, we have a lot more to say about that some other day, so let me go on. We'll spend a whole day just talking about cyclic groups at some point here soon. A couple other definitions I should share with you. Center of a group. What's the center of a group? We use Z of G for the center, and that is going to be A in G such that AX is equal to XA for all X in G. You can also talk about the centralizer of an element, G in G. And that is, we denote by C sub G, the centralizer of an element. Oh, I'm sorry, I've used C of X in my notes. Let me stick with that. C of X, centralizer of X. That is going to be G in the group such that they commute with X. All right. Both of these can be shown to be subgroups of a G of a group using the one-step subgroup test. It's not that hard. Pretty good test questions, both of these. In fact, I think another fun test question, or just question in general, is to show if you look at the intersection. If you look at the intersection, this can be shown. The intersection over X and G of the centralizer of X, the intersection of all centralizers, the common intersection of all those, that's just the center. Something that's the relation between the centralizer of an element and the center of the whole group. What's the center of an abelian group? Yeah, the whole group, right. We could say that a way to characterize an abelian group is just that it's equal to its center. Right. And likewise, the centralizer for any element in the abelian group is the whole stupid group. Yeah. Sorry. I know some of you don't say stupid in your house. My apologies. Let's see here. Getting back to permutations for a second, there's an important, you might wonder, so what's an important subgroup of permutations? It turns out, if you just look at the even permutations, it's pretty easy to see that the even permutations form a subgroup of permutations, right? Because if you take the product of two even permutations, it's still even, right? And if you think about the process of taking the inverse of a permutation, it doesn't change the cycle length, right? It just shifts them around, but the total number of transpositions doesn't change. Like a cycle and its inverse have the same number of transpositions up to, inserting and deleting copies of the identity, whatever. The point is, it's not hard to argue that the set of even permutations forms a subgroup, by the one-step subgroup test. In fact, the size of the even permutation, this is called AN. AN is a subgroup of SN, is what I'm saying. So this is the so-called alternating group. Don't ask me why. And this is the so-called symmetric group. Don't ask me why. I don't think that's at all obvious given our current discussion. But anyway, those are the labels. And in fact, the alternating group has half the size of the symmetric group. So its order is actually n factorial divided by 2. Fun fact, but I don't really want to prove that today. I'm just mentioning. In fact, a lot of the things that are written in this lecture, I'd just like you to read. In particular, example 2.4.21, 2.4.22. I've got some more detailed comments about the alternating group of order 4 or order 3, what that looks like in particular. I have some gory details there that I don't think writing them out is good. Now, the end of this lecture is about isomorphism. All right, so there are just a few theorems about isomorphism I want to share with you. So, isomorphism theorems. So let's see here. We're going to let phi be an isomorphism from a group G to a group H. We have the following things are true. So the center of H, guess what? It is the image of the center of G. So the image of the center under an isomorphism is the center of the isomorphic group. We also have that G is abelian if and only if H is abelian. I forgot to say something important. Be in what? Isomorphism. I said it in words, but I didn't write it on the board. That deserves to be written. That's important. If phi is just any old function, I don't get to say anything I'm saying right now. It's important that it's a bijection which preserves the structure of the groups. Now, once you've proved point 1, point 2 is pretty easy to get, right? If the center of the group is G, then phi of G is H by construction, because we assume that an isomorphism is a surjection, so its range is the whole codomain. So like once you know the first item, the second one follows immediately. Another thing that we'll learn, something we should know about isomorphisms, is if we feed an isomorphism a cyclic subgroup generated by A, well, guess what? That's the cyclic subgroup generated by the image of phi, of A under phi. So isomorphisms take cyclic subgroups to cyclic subgroups, and better than that, they take generators to generators. A is the generator in G, and phi of A is the generator in H in this equation. And of course, an easy consequence of what I just wrote is that G is cyclic if and only if what? H is cyclic. So what I'm trying to get across to you guys here is that the structure of the center and also cyclicity, these are properties of groups. I mean, what's a good property of a group? A good property of a group is something that's preserved under isomorphism. If something's not preserved under isomorphism, you might argue that it's not really part of group theory in some sense. By the way, since the order of phi of A equals to the order of A, and that's also equal to the order, now look at this, that's equal to the order of the cyclic subgroup generated by A. Do you understand the difference between these symbols? So here, this is the order of the element. If you look at it, the order of the cyclic subgroup generated by A is the same. You could prove that. What is in the cyclic subgroup generated by A? It's got A squared, A cubed, dot, 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 A to the n. That's equal to the identity. So if you look at it, that's n things if it's got order n. Otherwise, it's got infinite order, so the cardinality is, well, countable infinity, I suppose. And so this order of the element is also the same as the order of the cyclic subgroup which it generates. And so that allows us, I mean, this can be proved as follows. Well, I say if there's time. No, there's not time. All right, because I don't want to hurry what I'm about to do. This is, so these, the proof of these, we could go through. It's not that difficult. I mean, here I'll start to prove this one. How about that? So phi, how about this? Phi of A to the power k is what? We proved this last time, right? That's phi of A to the k. So thus, if x is an element of the cyclic subgroup generated by A, that implies that phi of x, well, rather, excuse me, yeah, phi of x, goodness, good night, I'm an idiot, A to the k, oh, brain broken, yeah. All right, sorry, let me just take a breath and prove this here. So let us focus on the proof of this right here. How will we prove this? Let's let X be an element of the cyclic subgroup generated by phi of A. All right, let's do that. Then what's that mean? X is equal to phi of A, parentheses to the k power for some what? For some integer k. Then what? Thus, X is equal to phi of A to the k. Where A to the k, of course, is an element of the cyclic subgroup generated by A. And that, what's that show? That shows that X is an element of phi of the image of this, because this equation right here shows that X is mapped to by something in here. And so I've just shown that an arbitrary element in here is also in there. What's that do for me? The cyclic subgroup generated by phi of A is a subset of phi of the cyclic subgroup generated by A. Now we can prove these sets are equal. We need to go the other way as well, right? If X is an element of phi of this, right, then that means that X is equal to phi of A to the k for some A to the k in here, right? K is an integer. And that says that X is equal to phi of A. I'm sorry, it's almost the same stupid argument, right? It is the same stupid argument. I mean, a more confident professor, or confident or competent, I don't know, you pick, would have just written this as a biconditional proof, right? Anyway, so there you go. That says that X is an element of the cyclic subgroup generated by phi of A, which then shows that this guy is a subset of that guy. We have the other inclusion, therefore the sets are equal. That proves the red boxed equation. All right, great. So isomorphism maps centers to centers. It maps cyclic subgroups to cyclic subgroups. It keeps generators. What else does it do? What else does isomorphism do? Now here's the really neat thing, is isomorphism preserves polynomial equations. Let me write that out here, if I can. Theorem, if you've got phi going from G to H in isomorphism, if B is an element of G and K is a element of the integers, then the equation x to the k equals to B has the same number of solutions in G as does the equation y to the power k equals to phi of B in H. The proof is given in the notes. Basically, you just hit the equation, assume one of them's true, hit the equation with the isomorphism. You get the corresponding equation for the image of the isomorphism, which says that the image of a solution is a solution to the corresponding equation. really the proof is literally just take phi of this and see that y equals to phi of x is the solution to this over here. That's the proof. The application to this is kind of shocking because, you know, if you guys were to ask without this theorem to prove the following, you have g is equal to the reals, non-zero reals, in other words, reals without zero, and h is equal to, let's say, the positive reals, right? Both under multiplication. Then you could ask the question, are these isomorphic? See, they're both infinite, so that's no help. And trust me, like trying to directly prove these are not isomorphic, it's really kind of a drag. I mean, I don't know what to do. So, I mean, this is what I know to do, is to study equations, right? So if there was an isomorphism, right, then we should be able to contrast x squared equals to 1 here, right? Where does 1 have to map to under an isomorphism? What's my phi of b have to be? It's an isomorphism. It takes 1 to 1, right? Maps the identity to the identity. So we'd have to study the equation y squared equals to 1 over here. If there existed an isomorphism, we could study both of these equations. They should have the same number of solutions, do they? What's this say? This says x is equal to plus or minus 1. What's this one say? Y is equal to 1 alone, because the minus 1's not in there. So we have the same equation, right? And when we study this equation in the different contexts, we have a different 2 solutions versus 1 solution. Therefore, there cannot exist an isomorphism between these two. Similarly, if you look at g equal to, say, rx, and h equal to the complexes, you can study the equation x to the 4th equals to 1. Right, versus y to the 4th equals to 1, and see the difference? X to the 4th equals to 1 has solutions plus or minus 1 in the reals, the non-zero reals, but y to the 4th equal to 1 has 4 solutions in the complex, non-zero complexes. In fact, those 4 solutions are our beloved 4th roots of unity, which I know you want me to talk about some more, but anyway. As you can see, that proves that the non-zero reals is not isomorphic to the non-zero complexes. Proving that without this insight, I don't know. Any questions? So I have tried to do my level best to cover the part of this lecture in lecture, which I think is absolutely most important for you to hear me say. But there's more in here for you to read, right? And I hope you're reading along. I think you are. So anyway, next up is our discussion of the dihedral group. So do you guys know what dihedral means? It means 2 faces. So the next